This is the NARI Sim Center's Live Expert Tips, where we cover diverse aspects of simulation and modeling in natural hazards engineering. Each session includes a technical example that demonstrates a feature of Sim Center tools relevant to research in natural hazards and their effects on the built environment. In this session, we introduce you to global surrogate modeling, and in particular, the Gaussian process-based variety. Global surrogate modeling aims for an accurate approximation of high-fidelity simulations across a predefined parameter space. And in today's session, Dr. Songri Yi will demonstrate this for a surrogate model of a 6-story shear building trained to predict the nonlinear response to earthquake excitation. Dr. Songri Yi is a postdoctoral scholar at UC Berkeley, where she develops novel methods for sensitivity analysis, multi-fidelity surrogate modeling, and adaptive design of experiments at the NARI Sim Center. Her research interests include probability-based sensitivity analysis, surrogate modeling, structural reliability analysis, and random vibration analysis. Thank you for being here, Songri, and we invite you to begin.
Thank you for the introduction, Matt. Thank you everyone for coming to this live expert tip session. Today I will present about replacing a computationally expensive simulation with a Gaussian process surrogate model. And for that, quoFEM tool will be used, which is developed in Sim Center. quoFEM stands for quantified uncertainty with optimization for the finite element method. As its name implies, we support some UQ and optimization engines through the software, and also an easy interface with the FEM application, user-defined FEM model. This can be written in OpenSys or any other programs. Our first impression could be you bring the FEM model and we do the rest. But in the end, what we aim is to have you more understanding on what is happening beyond the user interface. So we provide some references through tool documentation. And since we are open source project, we have our code all uploaded in GitHub. You can always download it, inspect it, modify it, and also even contribute it by making pull requests. And also we have Sim Center forum. If you have some new feature requests, or if there is some functionality you need in your research, but if our tool is not supporting them, we will be happy to hear and try to incorporate it. With that, I will begin with my today's presentation. I will first introduce you to very basics of surrogate modeling, and then move on to quoFEM, showing how this theory can be related to the information required in quoFEM. So I will start with what is surrogate modeling and why we do that. The motivation comes from computationally expensive high-fidelity simulation models. So when you have to repeat this high-fidelity analysis with different set of parameters, then you will want to have gain efficiency by approximating this high-fidelity response with less expensive model, which we call a surrogate model. How we do that? Let's consider an example. Consider we have a high-fidelity structural model, and there can be a couple of parameters that affect the response of interest. So whenever you run simulations with different combinations of these parameters, what you obtain is a set of samples in this 3-dimensional space. And if you repeat more simulations using more combinations of parameters, you will realize that all these samples lie on some kind of a mathematical surface in this 3-dimensional space. And we call this as response surface. So motivation is that instead of always running high fidelity simulations for new different set of parameter combinations, shall we just save this some kind of mathematical form of this surface and then call this function to have like efficiently predict the response or approximate the response of interest. So there can be many reasons of training surrogate. So if you have specific reason for training surrogate, it is called application-driven surrogate modeling. For example, if you want to perform optimization and surrogate is assisting them, and also you might want to run reliability analysis and using the surrogate modeling. So in those cases, there will be a domain in the parameter space that has higher importance. For example, if you are running optimization, then you will want to first identify which domain is likely to contain the optimal values, and then want to concentrate your simulations inside that domain. On the other hand, global surrogate modeling aims to have a general purpose surrogate model. So when you're in the training stage, you don't really have specific application in mind. So you just want to have minimum error, prediction error throughout over or entire domain. So you want to improve overall accuracy when in your training stage. So in this square, red domain, entire domain has like equal importance. So there are many approaches for training surrogates, such as neural networks and polynomial chaos expansion is also popular. In quoFEM, among them, we support Gaussian process model, and also we have a new feature, which is probabilistic learning on manifold-based surrogate modeling. And other than this, we also support some of the application-driven surrogate modeling through Dakota engine. So now I will go through, so our presentation today will focus on Gaussian process surrogate model, which is also known as a Kriging model. And so how does this Gaussian process modeling approximate the response surface? It's what I want to explain today. So the basic assumption it has is that this response surface is a Gaussian process. What does that mean? If you have a response surface, if you have some points on the response surface, it can be two or multiple, then it is the Gaussian process means that all these points are jointly Gaussian. So it means that the response at this point, whatever the y value is, will follow Gaussian distribution, and also the other point will have Gaussian distribution. And since they are jointly Gaussian, they will have some correlations. And another assumption is that this correlation between two responses increase as distance between the 2 points decreases. So consider 2 points in this figure. If they are far apart, the response at each point will not have any correlation. So if we draw that in using this joint probability density function, this x and y axis represents the response at 2 points, and their joint distribution will look like have some circular shape. On the other hand, if these points are close to each other, then they will have higher correlation, and that results in this kind of joint distribution, as we learned in some probabilistic theories. And if they are so close to each other, if they overlap with each other, they will be perfectly correlated, meaning if the y value at point A and y value at point B will be exactly the same. So in this correlation, in this probability distribution figure, that will be represented as a single diagonal line here. And whenever YB value is, whatever YB value is, YA will have the same value. So that was just the basic assumption of Gaussian process. And then I will talk about how it can help us approximating the response surface. So it can be done through some samples. So when you have samples, correlation helps you to reduce the prediction bound. So let me explain this with an example. Consider a structure model that has two parameters, A and E, like material and geometric parameters. And you're interested in displacement at the middle of the truss structure. If you run simulations for different combinations of these parameters, you will get samples like in these blue dots. And now you want to predict what will be the response at a new point X with new parameter values. To understand that, let's simplify this problem a bit. We will only consider two samples. First, consider sample 1. So because they are close to each other, they will have high correlation as we showed in the previous slide. So Y value at point 1 and Y value at point X will have this high correlation. So when you don't have any knowledge about the points, then you still have like high uncertainty when you want to predict Yx. You just know that Y1 and Yx will have some similar values. However, when one of these points are observed, meaning if we know what Y1 value is, say we have Y1 value here, then accordingly, the prediction of Yx will be updated. So because Y1 is located in this value, there are limited possibilities for Yx represented as this red PDF function. So you can see that the prediction, like average prediction, has been updated based on Y1 prediction, and also variance of prediction has been decreased. So we have tighter bound on, we have better idea on what value will Yx be. On the other hand, if we consider sample 2 and point X, they are far apart, therefore they don't have much correlation. And what that means is that even when Y2 is observed, we really don't gain much information from that. So point X value will be independent from what we had observed from Y2. So this concept can be extended to multiple samples, and Gaussian process basically kind of interpolates the response at certain point using the information around that of the samples located around this point. And here the question that can naturally arise is that then how fast will the correlation decay? So how far is like far enough? To answer this question, we need to, Gaussian process defines correlation kernels. That's nothing but a mathematical function that defines how fast will this correlation or covariance decay as 2 points in the parameter space increases. For example, Matarm function and exponential function are like two of the popularly adoptive correlation kernel when constructing Gaussian process. So first Matarm has this kind of mathematical form, and if we draw this in the as to the plot, we will see something like this. And there's also exponential function. For two of these functions, we see that there are two parameters. There's one that representing length scale, and there's one for shape parameter. So length scale defines how fast the correlation decays in average, and shape parameter defines the detail. So in this plot, they all have the same length scale, which is 1, but because of the shape parameters, some of them we can like specify detailed properties, like blue curve decays faster and then have heavier tail behavior. And depending on these details, we can expect different response surface property as well. So this figure on the right-hand side is a simple one-dimensional response surface example. So if you expect your response surface to be smooth enough, then you will probably want to choose the green curve in the both functions. So the common practice is first to choose the mathematical form based on engineering judgment, and also the shape parameter based on desired shape of behavior of response surface. And in many cases, we want our surface to be smooth enough. So therefore, value of 2 will be appropriate. And then the remaining parameter length scale can be optimized based on the data set. So this slide shows you some examples. So here, this example introduces exponential kernel, and you can see the shape parameter of 2 is chosen. And length scale is still remaining as a known parameter that we want to kind of optimize. And there are 2 additional parameters. First one is prior variance that defines overall variance level of the data set. And there is also another parameter that controls the noise level. So if you expect some noise inside the data, then probably you will want to have this value other than 0. So let me explain this through these 3 examples. So these 3 curves shows you the response surface constructed using the same data set and the same method, but their parameters are different. I would say the first figure looks kind of natural, and that means it is likely that these parameters are well optimized. On the other hand, if you see the second figure, you have much less correlation length. That means each observation has smaller influence range. Therefore, it's much less smooth compared to the first figure. And then also, if you look at this noise level, it assumes that there is almost no noise. Therefore, our response surface will have to go through all these observation points. On the other hand, if you see the third figure, first you will see that correlation length is much higher. That means we have very smooth behavior. And also we have 0. Like higher measurement noise level. That means the response surface kind of allows the data to be significantly off from what we predict, because that can be attributed to the noise in the data. So this figure shows you that depending on parameter you choose, we can expect very different range of response surfaces, and therefore also optimizing these parameters are important. So for optimizing this parameter, it is common practice to do it through maximum likelihood estimation. So this is basically following the assumption of Gaussian process that all these data sets are realization of a huge joint Gaussian distribution. So it's just trying to find what would be the best Gaussian distribution that is likely to produce these data sets. You can see the details through this nice textbook. And so I will now go through the review the Gaussian process, training process, and what kind of information is needed in each state, and how quoFEM asks the users to put those information. So the Gaussian process training workflow first runs a set of high fidelity simulations and then construct surrogate model and check whether we are satisfied with its performance. And if not, we run more simulations. So that's the basic overview. So we start with generating some initial experiments or samples. So here in quoFEM user interface, you can define how many number you'd like to start. If you don't have good idea, we provide some default values. And also in case you already have some simulation data set, you can start immediately using that data set instead of running simulation. So you can also import the data set if it already exists. And then based on data set, it runs simulations and trains surrogate model. Here training means we are calibrating the parameters like length scale and the noise variance and those parameters. And for this, we employed GPy package. This is a Python package that you can install as well. So the quoFEM user interface and backend application calls this GPy for the training stage. So in training Gaussian process, as we discussed, we need to first define what will be the correlation kernel we want to use. We provide some choices for that. And also we can define whether we want to include measurement noise, or if you know that there's no measurement in data, no noise in the measurement data, then you might want to set it to be 0. But sometimes it's nice to put it flexible to gain more numerical stability. And additionally, if you expect linear trend from the function, like from the data, then you can add linear function, and you can also try to train surrogate on the log transform space instead of the original space. And then once surrogate model is constructed, we want to check whether we want to finish the analysis or continue with new simulations. For that, we provide 3 exit conditions. First is the maximum number of model runs. Second is the maximum total computation time. So if one of these is reached, then it will end the analysis. And the third one is convergence criteria. So if we have enough accuracy, then we will also stop the analysis. So here we said it's normalized error. This is evaluated using cross-validation information. So basically we remove one data from data set and construct surrogate and try to predict the data value and compare it with the one we removed. So the detailed definition is provided in quoFEM documentation. You can find quoFEM documentation through quoFEM webpage or like where you download quoFEM, and also through the user interface I will show you later. And then if you are not satisfied with the performance of your surrogate model, then it is likely that you want to add more samples. For that, as you can see in this figure, as more samples are gradually added, our Gaussian process will be improved gradually. So we start with high uncertainty, and then as more samples we gain, we have better prediction, tighter prediction. And for that, we would like to put samples in a smart way instead of just randomly populating samples. This point can be selected based on variance measure. You might want to locate sample at where the variance is highest, or you can incorporate additional bias measure that can be obtained from cross-validation information. So we support some of these so-called adaptive design of experiments options. We have 4 options currently available. I will not go into detail in this presentation, but I'm planning to prepare another live expert tip to explain this. So this is more of the active research area. So that was the first part of this presentation. So I will go through demo from now on using this OpenSys structure model. So this is again overview how quoFEM can be used to train and use the surrogate model. When you have a structured data, structure model, you can use quoFEM to run any UQ and optimization analysis supported in quoFEM. Alternative way you can choose is you can train surrogate model first using quoFEM, and then later you can import this surrogate model to run this analysis. So inside quoFEM, there are different UQ engines, different methods, different algorithms supported. And here, what I will present today applies to those inside the surrogate modeling class. And once you train your surrogate at this stage, you can re-import them as in place of FEM engines and replace it for the further analysis. So this is the structure model we will use today. It's 7 degrees of freedom nonlinear structure system. We have 6 variables of interest, 6 parameters, like 5 parameters, and also we want to treat this scaling factor of ground excitation as a variable. And we are interested in identifying peak response of 7th story and the 6th story and the 1st story. So this is some dynamic response that can be obtained by Monte Carlo simulations. So we can see some nonlinear behavior. And this is actually from the previous live expert tip video. We have done sensitivity analysis using the very same structure model. And we have seen that PGA was the main factor that affects the response. And for some of the responses, FY was also affecting the response. So given that, I will now move on to quoFEM. So this will be the quoFEM user interface you will first see when you open up. And here I will first find SimCenter UQ engine because it contains this train surrogate module. And here I will use sampling and simulation instead of just using dataset. We have 3 criteria. I will set this to be 7 for quick demo. And I will keep max computational time to be 60 because it will finish before that. And also we have target accuracy of 0.02. And here you can set this correlation kernel. These are maternal class and exponential class kernels with different shape functions. So I will just leave the default one. And also you can set null-gap variances. Here null-gap variances can be understood as measurement noise. And for the FEM model, I have my script prepared in this folder. And this is also shared through Google Drive. This is the main script of OpenSys model. As you can see, the the script is pretty much same as what the ordinary OpenSys script is, but we have this new pset command to make quoFEM identify what are random variables. So otherwise, it's just ordinary OpenCL script. We import that first, and then we will import post-process script, although it is not always necessary. And then here you can see quoFEM has already identified what is written as pset and also read this value to pre-populate the bound. So it just read this value, treat it as a mean and give 10% lower and upper bound. So I'll just keep it this way. And for the quantities of interest, I will see node 2, displacement at node 2, acceleration at node 2, maximum displacement at node 7, maximum acceleration at node 7. So we will see this for quantity of interest. Only because we use this post-process script, it will read these QI names and give the result corresponding to these names, but this is not necessary. If your main script already produces the required outputs, then you don't need to have any post-processing script, and any name can go in here. So anyways, I will run the analysis. Yeah, so this is the result I got. So since we had only 7 samples, of course, normalized error is not satisfactory. This is red because it exceeds the target accuracy we had provided. So let's start with the beginning. So it says surrogate modeling completed. Process ended as the maximum number of simulation is reached, which was 7. So even though we didn't reach the computational time, it ended the simulation. And also the target accuracy is not reached as you see here. So this normalization error is based on leave one out cross-validation error measure. And this graph actually shows you the comparison between exact response and the predicted response based on cross-validation. So it's not bad. This is simple problem. And there are 2 other correlation measures, other measures such as correlation measure and R2 index. Here we see that for some example, it more struggles to identify the response. And then here is saving options. This is important when you want to use this surrogate model. So if you click the first button, it will allow you to save the surrogate model in terms of pickle file and JSON file. So even though it says only pickle, it will also save relevant JSON file, which contains like information on the surrogate model. And then the next thing you can save is kind of a report that shows you the status of training. So if you open up this file, it shows you some information, and also it shows you what was the final GP parameters that was optimized in the backend analysis. So for example, for the first response, we have this length scale parameters, which was denoted as L in the slide, and also overall variance as well as what is the noise variance level that is optimized. So even though I asked it to optimize the noise variance, they thought there was no noise in the data, so it is giving you almost 0 value. And then you can also save the parameter character set data parameter samples of the parameter values you use for training and corresponding response values. So this can be also viewed in this window, but we added additional saving button because it can be particularly useful when you want to continue training the analysis. So if you already run like 100 simulations, and if you are not satisfied with your response, what you can do is to import data, import the data point what you just generated, and then use that for further analysis, for example, by importing X and Y. And if you click run button, you can run further analysis. So now I want to show you the result for more simulations. I ran this morning with 50 samples. And here, all the options are basically same. I use the same kernel function, and this is the result. So all the other responses are pretty good, and even the acceleration approximation is not bad, but it does have some variances. So if you inspect this graph, this table, you can see that you can show pairwise scatter plot between any of these columns. So for example, you can see as factor increases, how acceleration will increase, and also comparison between exact simulation result and the surrogate model prediction results. And then now I will quickly move on to how to use trained surrogate model. I will use it for propagation. Before that, I just want to clear all the inputs. And then we'll not run too many simulations today. Here, instead of OpenSys model, now I want to read surrogate Gaussian process model we just constructed. So we put so I saved all the information through the that was about the surrogate model that was trained using 50 simulations. So first one, we need to import JSON file, which was saved when you click this save surrogate button. And then there's also picker file in the same folder. And here you can also set maximum allowable variance level. So if your prediction variance is expected to be very high, that means your prediction is likely to be not reliable. And then you can specify what will be that threshold and how you will handle that. You can just stop the analysis, or you can ignore and just decide to believe whatever surrogate gives you. Or the third option is that you can try running exact FEM simulation for only those that exceed this variance threshold. Say if we let's first do with ignore and continue. It also reads the information from the inputs and pre-populated distributions. But one thing we need to be cautious is that the sample that will be generated in this analysis is safe to be inside the boundary that we have trained. For example, we have trained this surrogate for these parameters in the range of between 90 and 110. So if we use this standard normal distribution, many of the samples will located outside of the boundary. So we don't want that to be happen, because there we will first have very result prediction with low accuracy, and it will say it has high variance. So instead of that, I will just use the same range what we trained and also the same distribution. And for the quantities of interest, it should be those what we have used for training. So here we provide a list of QI, so you can easily copy and paste all of them or some of them. So here I will see only the response of these two responses. First was very good in terms of surrogate accuracy. The second was a bit more struggling. So let me run this analysis. And it shows you the results based on the surrogate prediction. So here what I want to inspect is the bounds probably. So these blue points and red point are obtained from surrogate prediction, and gray point represents the prediction variance. So you might want to use this information, or if you want to choose other options, for example, you can run exact FEM simulation in case your prediction variance is expected to be higher than this value. In such case, if we run simulation, you will see that this one is slightly like the sample obtained using this analysis is different from surrogate prediction. That means it ran actual FEM analysis, high fidelity simulation, and also same for these samples. And for the other samples, since it has smaller prediction variance, I guess it decided to believe whatever surrogate output is. So if you want to inspect this in more detail, you can go to surrogate log file. It's located in documents folder, quoFEM, local work directory, and TemSim Center. Here we save all the results from every single analysis, and then gives you the summary of the results. Here it shows you that for sample number 7 and sample number 2, the prediction error was 3.11 and 2.33. So it was greater than what we have set at threshold. So it ran original high fidelity FEM model instead of trusting whatever came from surrogate response. So this is how you interpret the result. And finally, I want to give you a tip on validating the surrogate model. So we had some cross-validation errors, and we know that this is not perfect. It can be biased. So what we want to do is to test with a new test set of data that are not used for any kind of training. So for that, what you can do is to make it run exact FEM simulation whenever the prediction variance is greater than 0. That means it will always run exact FEM simulation, and if we inspect this result, we will be able to compare what is exact high fidelity result compared to what was produced by surrogate model. So this is the results we can obtain. Here we can see that all the predictions are off compared to what surrogate gave. So this gray square is always surrogate prediction, and this blue one is obtained from high fidelity simulation. But if you select another response, which we had a nice straight diagonal line when we inspected this exact versus prediction curve, in this case, actually, the prediction and simulation results will overlap with each other. So that's because surrogate is well constructed. So this gives you an idea on how well is this surrogate is constructed, so that you don't just leave it without any more information. So I think that's the demonstration part I have prepared. And then remaining is just the summary on upcoming features of quoFEM. So we will, now we plan to propagate this surrogate modeling to other tools such as EUQ, VUQ, HydroUQ, and for that we are trying to deal with multiple earthquake excitations by including stochastic rigging approach. So we are working on that. And there's model selection and averaging capability based on Bayesian theory. And also we are considering implementing global sensitivity analysis for high dimensional outputs. And also we are always interested in hearing from you. So please feel free to visit our Sim Center forum and give us your ideas. And finally, there are upcoming live expert tips. There are upcoming live expert tips. Adam will present about building level performance assessment using Pelican. There will be presentation about other surrogate modeling, which is plum approach. By Quanxi, it will focus on earthquake engineering applications. And there's another quoFEM live expert tip that will cover Bayesian calibration and reduced order model approximation. So I think that concludes my presentation. Thank you everyone for listening.
Thank you, Songri. That was really informative. I learned a lot in today's presentation, so thank you very much. There's a question for you. It has to do with the design of experiments option. The question is, does the none option for DOE method pick training data randomly? So if we have the none option selected, does it?
Yes, it's just randomly samples the training point.
Okay, and a follow-up question on the design of experiments method. Which method requires the fewest training data?
So they can have different answers, but I would say that IMSCW is the most efficient one in terms of number of training data set, but IMSC method itself takes some time to identify what are the optimal points. So there are some trade-offs, but if you only purely consider the number of simulations, then IMSCW should be the best because it tries to balance this between what we say exploitation and exploration property. So it tries to sample like where we don't have much information, but also it tries to concentrate more sample on irregular domains. And MMSCW does the same, but it's weak in handling boundaries. So usually IMSCW is considered to be also more robust. Would that answer the question?
Yeah, I think so. Another question, why did you select the Gaussian process as a surrogate model instead of another machine learning approach?
That's also a good question. So for example, there are different surrogate modeling methods. Neural network will be the most popular one, but we found that neural network requires a lot of data set. So I think strength of Gaussian process is that it performs reasonably well with when we have few data sets compared to other methods, because it has both interpolation property and regression property. And also it gives you the prediction bounds, as well as like not only just the most likely prediction, but also some prediction bounds. And that information could be useful. And especially because we are dealing with natural hazard engineering, we thought those uncertainty in the surrogate model should be properly propagated to the further analysis, for example, to the PBE analysis, to loss and risk assessment and so on. So for that, Gaussian process model was our first priority.
Great. And I think one thing I took away was in this example, you had a factor on the ground motion. So the intensity measure of the ground motion was encapsulated in this surrogate. It was a feature of it. Is that always the case, that maybe the event is a component of the surrogate model? Is there any way that you can create a model that isn't dependent on, say, in this example, a single ground motion?
So you mean when we have multiple ground motion sets?
Sure. If you were to apply a different ground motion than the one that was used to train the data, or train the surrogate, what are the approaches to be able to do that?
So for that, it becomes much more tricky, because now we have excitation time history as a random variable, which is really high dimensional random variable. If we think of discretizing this time history and considering it as single parameters or a variable of this surrogate function, then the problem can be high dimension. But another approach to deal with this problem is by introducing considering that as a noise. So instead of considering this excitation as a variable, we just want to treat the variability coming from different earthquake ground motion as a noise in the data, and then try to just identify what will be the mean and variance corresponding to that. And there can be approaches to reduce this prediction variance by extracting some features from the excitation time history, and then try to map between feature and the structural response. Would that make sense?
Yeah, it does. Well, I think that we're almost at our hour, so I want to thank you once again, Songri, for the presentation, as well as the example, and for answering these questions. Thank you to the attendees for joining. As a reminder, sorry?
I have one more thing. So
okay.
When we scheduled this live expert tip, I didn't know that today was our new version release date. So we will have new version, which has quite some changes, especially in the user interface. Today, if it's not already there, so please update your quoFEM version. Yeah, that's it.
Okay, that's another excellent tip. Thank you. Right, so as a reminder to the viewers, you can register for other live expert tips on our webpage, which is simcenter.designsafe-ci.org. And this concludes today's live expert tips with the NARI Sim Center. We hope you've been inspired by Songri to pick up the quoFEM tool and get to know a little bit more about surrogate modeling and the capabilities that she's presented today. So thank you again, Songri.
Thank you, Matt. Thank you, everyone, for attending.